So I want to talk about sorting permutations, and the difference between this talk and previous talks, well, not previous talk, previous research in this area is that we assign a cost to objects, to transposing different objects in our permutation. And so permutation, I'm sure you're familiar with, but a short review. You can consider the permutation as a tool, in two lines. The first line is the numbers from 1 to n, and the second line is a rearrangement of those numbers. And you can consider this as a bijective function where the image of every element is written below it. For example, if you call it pi, pi of 1 is 10, pi of 2 is 8, and so on. And so this is a bijective function from a set to itself. And for like any other bijective function, you can have its functional digraph. In a functional digraph, there is an edge from every element to its image. For example, 3, the image of 3 is 5, then there is an edge going from 3 to 5. So it's easy here to see that the functional digraph of permutation is going to be a set of disjoint cycles. And the reason is that the in degree and out degree of every element here is equal to 1. And so there is also the cycle decomposition of a permutation. You can write it as this, like this is obtained from these disjoint cycles here. This one corresponds to this, and this one to this. And so the next thing I want to introduce is transposition. Transposition is basically swapping two elements in a permutation. So for example, here you see 3 goes to 5 and 7 goes to 2. You transpose 2 and 5, then 3 goes to 2, 7 goes to 5. From just this example, you can see that if you transpose elements from within one cycle, you're going to break that cycle into 2 cycles. Here, 3, 5, 7, 2, it's going to be 3, 2, 7, 5. And converse is also true. If you transpose elements from different cycles, then you're going to combine them into one cycle. And one more thing, a transposition is usually shown by those two elements inside a pair of parentheses. So a natural question here to ask is that given a permutation, what is the smallest number of transpositions that you need to sort that permutation? And the answer comes from that easy observation that we had in the previous slide. So the identity permutation has n cycles. The permutation that we have, let's say, has k cycles. And then you do this to break the cycles into 2 cycles and increase the number of cycles one by one. So using n minus k transposition, you are able to sort that permutation and reduce it to the identity permutation. This result is actually pretty old. It's 1860 by Cayley. So you need n minus k transpositions to sort a permutation with k cycles. If you have any questions, please ask. So decomposition is just very similar to a sorting. A decomposition is a product. A decomposition is a product of the transposition that gives you the permutation that you want, and the sorting is the inverse process. So if you apply a sorting to a permutation, you're going to get the identity permutation. And so in the usual sense, each transposition is counted once. And you're usually looking to find the shortest decomposition with the minimum number of transpositions. But what we want to do, because of the applications that it has, is assign a cost phi ij to every transposition. And now we want to find the minimum cost decomposition of a permutation. This has several applications pretty much everywhere that you're dealing with permutation and sorting of permutations. These are some examples here. I'm going to just show you rank modulation in flash memories. So in flash memories, the way that you encode your information is using a permutation. These are different cells in your memory, and they have different charges. You rank the charges. For example, this is the highest charge, this is the second highest charge, and then you get a permutation for the cells that you have. But these cells have different leak rates. So for example, suppose that cell 1 has a high leak rate, then its charge is going to drop after a while. And then you'll see it's no longer the third element, it's going to be the fourth one. So if you look at the corresponding permutation, then you see that 3 and 4 are swapped here because of this charge has dropped. So basically, this is one case that permutations are coming to place, and you have this permutation. You want to find another permutation that has the shortest distance from this one. So now I'll give you one example that shows the short decomposition is not generally the best decomposition. Suppose that you have this cycle from 1 to 5, and then you have this cost function here. You can show that the shortest decomposition has cost at least 8. It uses 2 of these cost 1 transposition and 2 of these cost 3 transpositions, so you have cost 8. But the minimum cost decomposition has actually cost 6, but that one uses just one of these cost 3 decompositions. It has a longer length, but a shorter cost. So this one on the first case, this is a short decomposition. The minimum cost short decomposition is, for no apparent reason, we call it MLD, and then the minimum cost is called the optimum. Well, there is a reason, it's just not seen here. So now our approach to this, to solving this problem is going from the easiest case to the hardest case. First, you just imagine you have one single transposition and you want to decompose it. Then you move on to cycles and then to permutations. So for transpositions, the key idea is that you replace each transposition by decompositions of length 3. And we have efficient algorithm for that case. And I'll show that what's the use of just doing this operation, why this is sort of limited, but it's useful. I'll show you why. And then the second case is that you move on to cycles. For cycles, we found out that it's difficult to find the optimum solution. So we use the MLD as a bridge to take us to the optimum sorting of the permutation. And finally, we go to permutations. For permutations, we have 2 different methods. One of them is just a generalization of what we did for cycles, and then there is a heuristic method that can give you better results. So let's just look at the first case. You have one single transposition. For this transposition, a transposition has an odd parity, which means that every decomposition of that transposition is going to have odd parity. So the cases are the trivial case, every transposition, its own decomposition. Then you can decompose a transposition AB by using an auxiliary element C. And so if this condition is satisfied between the costs of these elements, then you have found a decomposition with a smaller cost than the cost of AB. And then you can have decomposition of length 5, 7, etc., which is the hard case. So what we first concentrated on this case and show that it has good properties. How much time do we have? Okay. So to find, so this is an algorithm that we call the triple optimization algorithm. In this algorithm, you first order your transposition in the increasing order of cost, and then you start from the top. You use each pair of transpositions to get a smaller cost for a transposition with higher cost, and you do this in a certain way, in an efficient way, and finally you'll get the solution that you get that is optimized. You have optimized the cost of each transposition among all those decompositions that can be obtained by just replacing every one transposition with a triple. So first AB, for example, is replaced by AC, BC, AC, and then this middle one is replaced by this triple here. So obviously this does not cover all decompositions of AB, but the minimum cost that we obtain this way will eventually show that it's actually the minimum cost of that transposition. So to see why that is correct, let's take a look at, for example, 5 decompositions of a single transposition. And so there is one really useful object, a representation for any decomposition. That's a multigraph, and this ties this problem to graph theory, and then you can use results from graph theory that basically make your life much easier. So suppose that you have all these elements here, and for each transposition in the decomposition, you have one edge in the multigraph. So let's say this is a decomposition that you want to find this multigraph. There are two edges from 1 to 3 here, and there are two transpositions in the decomposition. So now, if you look at the decompositions of 5 decomposition of a single transposition, you'll get some different multigraphs. But the good thing is that you can show that all these multigraphs represent decompositions that have cost higher than the cost of what you obtained with your triple optimization algorithm. So basically, this is we say this in the term that the triple optimization algorithm actually finds the optimum cost among all the decomposition of a single transposition. And an additional point here is that the proof actually shows that you can have alternative approaches. For example, you can use shortest path algorithm to find the optimum decomposition. Now, let's move on to cycles. So like I said, for cycle, optimum decompositions are difficult. We use MLDs. Now, just recall that MLD is the minimum cost decomposition among the decompositions with minimum cost. Sorry, among the decompositions with minimum length. So you have all the decomposition with shortest length, then you find the minimum cost among those. It turns out this is actually not that difficult. You can characterize all the MLDs using that multigraph of decompositions, and then there is a nice theorem that characterizes those multigraphs. Those multigraphs are actually trees that are planar inside the cycle that you're looking at. And this characterization limits your search space. Then you can actually look for the MLD, look for the minimum cost decomposition among all the decompositions that you have. And so there is an efficient algorithm to find that. We use a dynamic programming algorithm, which is a polynomial. And so now the question is, now that we have the MLD, can we use it to obtain a bound on the optimum solution, or can we, or is it the optimum solution? Well, we actually saw that it's not going to be the optimum solution in the first example, as I showed you. But what is the relationship between this object and the optimum solution? Again, we introduced another new object. It's actually really nice and small. So you had transposition in which you transposed one, you took one object to the place of the second one and took the second one back. Now just imagine you do only half of this, which will make it easier to do this operation because you don't have the limitation that you have to move both objects at the same time. And then give that object the cost, half of the cost of the original decomposition. Now in this case, you just have a bit more freedom. Right? You can move objects without having the limitation of a transposition. And so it's easy to see, I mean, I guess I just proved it, that the optimum decomposition is going to have a cost higher than the minimum cost of if you're using half transpositions. And we can also prove that the cost of MLD is at most is bounded by 4 times the cost of the half transposition decomposition. So putting these two results together, then we get to the main result that MLD is at most 4 times the cost of the optimum. So although we can find the optimum solution, we can find an approximation, a constant time approximation, which it's obtained efficiently. Now, there are cases that MLD is actually the best thing that you can get, and that's characterized by the cost function that you have. One example is that if you have a metric path cost with a certain definition, then you can have easier algorithms to find the optimum. And in these cases, the optimum is basically the MLD. OK, now, OK, I guess we're getting pretty close to lunch now. So moving on to permutation to the general case, you can see we can have 2 different approaches here. One of them is that we can extend the results that we had for different cycles. Now, you had MLDs for all those cycles in your permutation. One way is just to put all these MLDs together, and then that gives you a solution for sorting that permutation. And that's the same bound that we had there is going to hold here. And then for that specific family of costs that I talked about, then they are again equal. But there is another way, a heuristic way. Before you find the MLD, you can combine all these cycles into a big cycle. You do some additional, you apply some additional transpositions between elements of different cycles, and then you turn it into one big cycle, and then find the MLD for that cycle. It turns out that sometimes that approach gives you a better result than finding the MLDs of separate cycles and then putting the result, just saying that the result is the sum of those MLDs. So to summarize what has happened here, first we look at transpositions, and we find the optimum in polynomial time. Then we move on to cycles. For cycle opt can only be approximated using the MLDs, which are found in polynomial time. And for permutations, then we have the same thing we had for cycles, but we had an additional heuristic method that can give you sometimes better results. Thank you.